Okay, we've got a combined cycle, air on the top, steam on the bottom. Lots of stuff is given. Basically, I know the temperature, so I can look up H for each of the steam values. And I know basically what goes into the turbine and out of the condenser, so I can look at H up values for those. Now I've got efficiencies on my turbine and my pump and the steam cycle, so I'm going to have to do what we do with isentropic and efficiencies to figure those states out. But first I'm going to go through and look up most of these because I've got data that gives most of them. So go ahead and start with H1, which is 300 Kelvin. You can see that H is 300.19. So 300.19. State 2, temperature is 690. So I go 690, and I get an H of 702.52. So I get 702.52. Then H3 is 1580. So that's going to be on the next page, 1580. And I get an H of 1733.17. So 1733.17. T4 is 900, so my H value at 900 is 932.93. So I put that down, 932.93. And then T5 is 400, so I go and I look up my H value, and that's 400.98 given right there. So 400.98. So those are my air values. I've got all of those, and the only two steam values I have are H7, which is 100 bar at 520 degrees Celsius. So I go to my water table, and I'm going to 100 bar and 520. Now, for this one, I need both my H value, which is 3425.1, and my S value, which is 6.6622. So I'll go ahead and jot those down. So again, 3425.1, and S was 6.6622. Okay. Now the other thing I know is coming out of the condenser, I know the pressure is 0.8 bar, and I know it's a saturated liquid. So I go to, 0.08 bar. So I go to 0.08 bar, and I get an H value of 173.87. Is that right? Yep. And, 173.88. I need enthalpy, okay? And then I also need my specific volume because I'm going to do the pump, which again is V delta P, which is 0.00100, something really small. Go ahead and jot those guys down. So that's going to be, H is going to be 173.88, and then my volume is 0.001 0084. Okay. So again, now what I do is I'll go over here to kind of do some of these other calculations. Okay. I'm going to go ahead and find 8. Now, what I have to do is I have an isentropic efficiency. So the first thing I have to do is, okay, well, I know that, P8 is 0.08, and I know S8S. The ideal entropy would be 6.6622, which gives me an H8S of, well, I go to 0.8. I see that I'm within saturation because it's a high here of 0.8 or 8.22. I'm at 6.66. So I do the interpolation, and I find that my enthalpy is 2084.1. Okay. Then I use the fact that my turbine efficiency is my actual output, which would be H7 minus H8 all over H7 minus H8S. And I know everything here. I know the turbine efficiency is 85%, and I know all of my H values except for H8, which I will go ahead and write down as 2285.3. 2285.3. So that sets state 8. Now I have to go to state 6, right? So I'm going to use the pump. Remember, the work of the pump is basically that volume, which I'll call V9, times the change in pressure, which is going to be P6 minus P9. And what that's going to equal for an isentropic pump is going to be H6S minus H9. And again, I have to find the ideal case and then use the fact that it's 80% efficient to find the actual. So H6S then becomes 183.4 because I know everything here. I know my pressures and volume. I know H9, looked that up. Okay, so I can find H6S. Then I use my pump efficiency, which is just basically the flip of what I had before, which is going to be H6 minus H9S all over H6 minus H9. From that, I can find, oops, I put the 9 in the wrong, or the S in the wrong spot. H6S should be here. Okay, so H6S minus H9, anyway. Doing that, I get an H6 of 185.78. Now I have completely set my states here. Okay, so the next thing I need to do is I need to deal with my mass flows here. Okay, because I basically know Q out of the air is Q into the turbine, right? Okay, so I'm going to find the mass flow of the air because I know the power output of the gas power cycle. Okay, so that gas power cycle is 147 megawatts. So that is going to equal the mass flow of the air times basically the turbine minus the compressor, which is going to be H3 minus H4 minus H2 minus H1. And again, what I know here is I know this is 147 megawatts. Okay, and I know all my H values, so I can calculate the mass flow rate of the air. That mass flow rate of the air is 369.43. And that's going to be kilograms per second. Now I need to use that to help me find the mass flow rate of the steam because, again, Q out of the air is Q into the steam. So, again, if I take that mass flow of the air times H4 minus H5, that's Q out of the air, that's going to equal the mass flow rate of the water, the steam, times H7 minus H6. And again, I know all my H values. I know the mass flow rate of air. Therefore, I can find the mass flow rate of the steam, or the, I guess, what I call it, water. Mass flow rate of the water then is 60.67 kilograms per second. Okay, now that I have my mass flows, now I can easily find the thermal efficiency of the plant, which of course is work of the cycle over Qn. Well, I know the work of the gas that was given, plus the mass flow rate of the water, and of course that's going to be the turbine minus the pump, so that's going to be H7 minus H8 minus H6 minus H9. All right, so that's the 147 megawatts. This is the turbine minus the pump on the steam. Divide all that by Q in, which is going to be the mass flow rate of the air times H3 minus H2. Again, I know my mass flows. I know the work of the gas turbine. I know all of my H values. I can very easily then find that my efficiency equals 56.6%. So as per usual, go set your states. Once your states are set, figure out your mass flow rates using, I did it using knowing the gas output, and for the steam, I know Q out of this equals Q in of that. Once I have my mass flow rates, then I can use the mass flow rates as well as my enthalpies to easily calculate the thermal efficiency.